Hi everyone, welcome to Achieving Peak Performance with Register Allocation. I'm Joachim Schmidt. I work in the Zig core team and among other things, the register allocator in the Zig compiler. So yeah, who of you knows of this fractal? What this is? Okay. So it's basically a very simple equation that delivers us this very interesting and beautiful fractal. It's a few lines of Python code. How do I know that? Because I wrote it down. It's very simple. You go over the image like in X and Y axis, and then you have a while loop. You square a complex number, add a component to that, do that, and if it goes crazy, if it goes like to infinity, you say, oh, this pixel is a white pixel, and if it goes, if it stays bounded, this pixel is a black pixel. So let's implement this in Zig. It's basically the same algorithm. I mean, who of you has seen Zig code before? Okay, about half. Okay, perfect. So for those of you who haven't seen Zig code before, Zig has a C Rust-ish inspired syntax, so curly braces for scopes. You have static typing, which is not there in Python. You have, it's in general more explicit, so you have into float conversion is, you have to say that you want to convert it, and yeah, it's a bit more verbose, but it gives you more control. So, I mean, when you compare these algorithms, they look basically the same. They should be very comparable in performance, right? So let's. Someone wanted a benchmark, so let's give them a benchmark. It turns out for Zig is for 200 times 200 square. It's so fast it barely even shows up, and for a 1000 times 1000 image, it is faster than Python for the 200 times 200 image. So, what's the deal? How does Zig do this? Most people would say it's because Python is an interpreted language and Zig is a compiled language. What does it mean? In Python, you have the source code, you compile that to bytecode, which is then, it's compiled on the fly by the Python interpreter to bytecode, and then the Python virtual machine executes that, but it's not directly executed on your CPU. Whereas in Zig, it's directly executed in the CPU. So what does it take for this Zig program to be directly executed on the CPU? Let's inspect this executable. And we see some cryptic machine code. So these are the instructions that the CPU will execute for us, I guess. And the first word is what the CPU should do, and the other parameters are which operands it should use for this instruction. What we already see here, there are these variables that are used in these instructions are kind of weird. So let's look into the CPU and look why this is the case. And we will see, disclaimer, very simplified, we have a fixed number of registers, and we have some hardware components which can add, take a value from register, add them with another register, and put it back to a register. And you can move some data from the main memory to the CPU or to the hard drive or something like that. But crucially, it only operates on this fixed set of registers, which is fixed, so it's only a finite number, it's not infinite. And so let's do this ourselves. Let's take our Mandelbrot example and compile that to machine code ourselves, which means it's time to play register allocation. We have, for example, our simple squared norm function, which we use to determine whether our iterated number is out of the bounds or not. So let's try to allocate this to registers. So this is the UI to our game. We have here at the bottom left, we have the original function, which is just there for reference. We have a shop where you can buy machine code instructions. You may notice that the multiplication instruction is a bit more expensive because the CPU needs to work a bit more. And we have two registers available for us, R0 and R1 in this case. So how do we proceed? So in our original function, we have two multiplications and one addition. So I guess we'll buy two multiplications and one addition. And then we already know that we want to add the result of the two multiplications together. And we already know that the real part is in R0, the imaginary part is in R1. This is what's fixed by our CPU API. So this is also inspired by the real world. This is also a thing in the real world that the inputs and outputs are allocated to fixed registers. We can change that. But where we can change is like what register A will be, or like the intermediate results we use. So let's so this code, we can't give that to the CPU yet. It doesn't have like the fixed register, so it wouldn't know what to do. So let's try to make this valid machine code. First of all, let's allocate register A. Can we use register R1 for this, for the allocation of A? No, because we need R1 here later, and we would overwrite that. So R0 looks fine, so let's say A is R0. Then next, B. B, R0 doesn't work. We would overwrite the value of the first multiplication, so let's choose R1. So, finished. Perfect. We can give that to the CPU. CPU can calculate the norm. So, that was the first level. Now we'll go to the second level, which is a bit more advanced. So now we have to deal with complex multiplication. I don't know if you remember, in the iteration we had z equals z times z plus c. So there was a complex multiplication in there. And complex multiplication, a bit complicated. It involves 4 multiplications, 1 subtraction, 1 addition. So let's see if we can manage. So once again, I'll blend out the spec so we have more space. And I've already assigned like some placeholders for the variables here. And once again, the inputs and outputs to a function are fixed. So they have to be R0 and so on. And the outputs have to be R0 and R1. And this time we have 4 registers available, by the way. So yeah, let's go on and allocate like we did last time. So E. Can we use R0 for E? No. Sadly, no, because we need it in we need the existing value of R0 in H. Can we use R1? Also no, we need it in F. Can we use R2? Also no, we use it in G. Can we use R3? Also no good, F. So what to do? It's impossible. Maybe some of you have noticed this anti-pattern in our game, the show more button. Let's click that button. Oh yeah, before I have this analogy which just came into my mind. This is like as if we had a bucket full of registers and we put the values into the bucket, but the bucket was too small to fit all these registers, and we need to make space in this bucket. So we need to spill the bucket. And to do that, let's see what this show more has to offer. It turns out we have an infinite stash, theoretically infinite stash called the main memory of the program. And we can just temporarily save some registers there and then get them later. What's the drawback? It costs a lot. These instructions are expensive. They cost 100 bags of money. And but I guess we'll have to deal with it because there's no other way around it. We don't have enough registers. So let's split our function into 3 logical parts. First calculation of the real part, imaginary part, and then we combine the values. So my intuitive solution for this, I mean, you may have a different solution, but I'm going to quickly demonstrate my, one solution I had in mind. So the thing is, we have 4 values here, which we need later on in the computation here. But we create 2 new values, so we need 2 new registers worth of space. So we need to, from these 4 values, we need to save 2 of them and restore them later when we calculate G and H. So let's do that. Let's, for example, stash R0 and R1. So stash them here, and then later on grab them again from our stash. So now we still have a problem because E and F are 2 more values than the 4 values used here. So we also have to stash E and F. So let's stash E and F and then restore them when we calculate the real part. So there we go. And now we have a complete function, which not complete yet because we still have the placeholders, but we have a function which can use all of the registers and doesn't lose any information. Sadly, at the cost of these expensive stash instructions. So let's try to allocate E. And this time around, it's way easier. It's possible now. For example, we can use R0 and stash, like R0 is not used in the calculation of F, so we can put this value in R0, restore it here, and then yeah, everything works out. So let's use R0 for that. And equally also for all other placeholders, this now finally works at the cost of these stash instructions. So how do we teach? So what we just did is basically what every C or every compiler for native machine code does in the background. But how do we teach a computer to do what we just did, like in our brain? And it turns out there are 2 main approaches for this. One is a rather simple approach called linear scan, and one is a more complex approach. So the first idea is when we have, like, for example, this sequence of instructions. We have the point in our program where a value is first created, and then we have the point where it's last used. And so we can, like, draw some intervals of these. For example, A is calculated before somewhere, and then last used in E. B is calculated, used last in the first instruction, and so on. And the idea is, when 2 intervals don't overlap, they can share the same registers. If they do overlap, it means that the program uses both values at the same time, so they can't be in the same registers, otherwise they would mess the data up of each other. So we have these intervals, and now we can smash them together, like try to yeah, have like a greedy algorithm which uses them as best as possible. And what we turn out is that, for example, A and E can share the same register, B, C, and F can share the same register. And what we basically do is we have these intervals, and we go from left to right, and we allocate the first column to register 0, and so on. And if we run out of registers, all the intervals that are on this side will just be allocated to the stash. But this has a drawback. It's a pretty simple algorithm. The drawback is it's not always optimal. What is always optimal is when you use graph coloring. So here we say, okay, every placeholder here is a node in our graph, and every time 2 values exist at the same time, we add an edge between them. So then our graph would look like this. And now we say, okay, we have a interesting problem in mathematics called graph coloring, where we assign a color to each node with the idea that two nodes which have a link between them are not allowed to have the same color. This translates perfectly to our register allocation example, because when two values coexist at the same time, they're not allowed to share a register. So we can color our graph here, and we have a similar example, have a similar allocation than before. But in many cases, this performs better. However, graph coloring is NP complete. And you may have noticed like this creative task of having having a small number of stashes in our program is pretty hard, and it turns out it is NP hard. So what in practice compilers do is they have a heuristic for this. So they won't always have the best coloring, but they will have a good enough coloring. Yeah, so this is only a basic overview of register allocation. There is much more. If you're interested, you can check out the Wikipedia article for that. LVM and CraneLift have register allocators. Chris Fallon works on CraneLift and has an excellent blog series on there. Whoops. And yeah, the Mandelbrot benchmark was taken from the programming language benchmarks team. And you can check out the source code of my code examples, which weren't that many, but if you want, you can check out them in the repo linked here. Yeah, thanks. That was the talk. Yeah.
Wander around the microphone
Yeah.
again.
Joachim. Okay, so one thing though. He gave, so since people want benchmarks, and this one is actually a benchmark that interested me as well, that Joachim decided to not put in his presentation, but I will graciously give you the juice. So you have 5 seconds to think. Which is faster, Go or C#? Think. Okay, raise your hand if it's Go, in your opinion. Lift your hands. Okay, hands down. C#? I think C# has it. I think that C# people are right. I don't have hard evidence on hand, but here's an interesting thing about Go. Or rather, one small point. I think C# is faster than Go, but I think the average Go program is much faster than the average C# program out there, because there's a bunch of garbage written in C#. Anyway, one interesting detail is that the Go doesn't use LLVM. It is everything done in-house by them. And for a very long time, every time you would call a function and you are passing arguments to that function, they would never bother to try and stash these, overloaded term. They would never try to put these values inside registers. They would always default to stashing them on the stack. That's expensive. So that is a change that landed in Go 117, maybe, one of the recent ones. I might be off with my Go numbers, but like one of the fairly recent releases of Go introduced for the first time using registers to save function arguments passed to function calls. And that had a pretty big performance improvement. So, so what Joachim is showing here has to happen for everything, not just function arguments. But even just function arguments gave I don't remember the exact number. They do say the number in the release announcement, but it was pretty significant. So yeah, funny detail. That's it. Okay. Questions? No, it's not connected to the laptop. No worry. Okay. Is it right? Yeah. Go for it.
Okay. Yeah. Questions? Yeah.
So how does Zig do it?
Okay, so Zig at the moment uses the LVM backend, and LVM has different register allocators, has a greedy register allocator, but for the optimized release mode, which is what I use for the benchmark, it uses a graph coloring approach. Yep.
Why are you working for Zig and not for LLVM to optimize it for everyone who uses LLVM?
LLVM already has very good register allocation, and what we aim for in Zig is a fast register allocation. So it's not necessarily a good one from the runtime performance standpoint, but for debug builds, you want pretty fast compilation speeds. Also, when we work towards hot code reloading and yeah, just fast debug builds, because even in debug mode, LVM is already the bottleneck for Zig builds. So with our self-hosted backends, which is what I'm working on, yeah, an alternative fast register allocator is what I'm working on. Yeah.
Does that mean that you're register allocating like the allocation algorithm that you want to use, especially if you're trying to do like hot reloading, is going to be deterministic?
Yeah, most algorithms are deterministic. So like the algorithms I covered here are deterministic, and the ones we plan to employ in the compiler would be deterministic.
Is the algorithm agnostic to architecture, let's say Intel architecture or ARM?
Yeah. So yes, in general, yes. Of course, the architectures bring a lot of constraints to the table. For example, in ARM, there are some instructions which only need a specific set of registers, which can only operate on some of them, and the register allocator needs to take this into account, so it can't allocate a register to an instruction which this instruction can't actually use. So that needs to be like built into that algorithm, but in general, yes, these approaches are like target agnostic, so these work on basically any target that has registers.
Do you reorder instructions to make like the linear approach more efficient in some cases, if that's possible?
No, at the moment, our like the main focus of the Zig compiler self-hosted backend is debug compilation, and as such, compilation speed, and we don't consider optimizations to the to the intermediate representation yet. So if like reordering is built in one day, it would be probably before the register allocation. Yeah.
I guess like what kind of speed up are you looking for in terms of, I don't know, like order of magnitude or something, like if you, in the ideal case?
That's always hard to say. I mean, I have a rough idea of like Andrew mentioning that like 90% of the compile time or something like that, ballpark figure, is spent with LVM in debug builds, and in release builds even more. Like semantic analysis and stuff is basically compared to the LVM part of generating code is basically negligible. But we just plan to bring that down to a very reasonable amount. So like that even larger projects can hot code reload in fast.
For incremental compilation, the goal is less than 1 millisecond. On a decent computer, also, but arbitrarily called large code bases.
I don't want to hog time, but this is not only coding. We also do linking incrementally. So we can actually go really fast. They're not separate things.
To pick up on that, wouldn't it be possible to improve LLVM instead of trying it on our own?
Would be possible. There are also already numerous efforts on making LVM faster, but it's just it's a very large project, and it's very modular, and it has like the it already has like in itself, it's already a very complex project which already has like much thought put into it for optimal resulting binaries. Like it's not really geared for compilation speed, really. I mean, there are like as far as I understand, it wasn't like really intended as like a super fast compiler, but like a very good compiler. And there are efforts on like the greedy register allocator, which was added later, and various faster instruction selection mechanisms, which make code generation faster. They are on the way, but it's still with those enabled, we wouldn't like see a huge performance improvement, which we can do if we control the whole code generation phase.
Also, LLVM has to work with other languages. Like we have the opportunity of optimize our incremental build for Zig semantics. With LLVM, it would have to be much more complicated.
I think a better comparison is with CraneLift than LLVM, because CraneLift is faster. LLVM is more modular. It was never I don't think they ever wanted speed. They always wanted optimization, so runtime performance, right? And still, they base everything on the fact that LLVM always outputs an intermediate relocatable object file. Zig, the self-hosted one, does not. We immediately output into the binary. We don't go through intermediates, ever.
There's a blog post that I wrote, but that covers this point. It's called, if you search Zig LLVM, I think the title is Zig's new relationship with LLVM, and in there you can see our plans for incremental compilation and also a short demo. I think there was a question behind there before.
Was there? I didn't see any hands up.
Oh, come on, don't be shy. Oh no, we lost it. We lost the question. No. Okay. All right.
I just wanted to add, for everyone that's interested in this topic, there's a lot of stuff going on in the WASM space, because WASM in effect is like another language, like an intermediate representation, but at the same time a language of its own. And there's a lot of stuff going on there in optimization and what people can do there and how to push it. Because especially cloud providers are right now pushing for a way to push WASM directly to the cloud and optimize it there to the platform. That's something that you usually would only do like in function as a service with JavaScript or Python.
Perfect.